Dear friends, this is my tutorial 21 in Gaussian. So in this tutorial you are going to learn how to do UV visible spectra calculation using Gaussian 09 or 16. Okay, so this is the UV visible spectra of this organic donor acceptor dye. So I calculated using TDDFT method. Okay, so this is the paper published in Journal of Physical Chemistry C. In this paper they used this dye. They calculated that absorption spectra, so we will also do that absorption spectra using our method, and we will compare with this one. Okay, so this is they are calculated UV visible spectra with different functional they did. So we are going to use only B3LYP spectra functional with ethanol solvent. So they did only they did in the acetonitrile solvent. Okay, so we may not get that much big difference, so we will try to calculate the ethanol solvent. Okay, so this B3LYP graph is so this one. So you can see the round model one. This is the one B3LYP model UV visible spectra. Okay, so we will also do and compare with this result. So before going to do your UV visible calculation, you need to optimize your donor acceptor dye. Okay, so I will show you the input and output files for this geometry optimization using Gauss view. Open your Gauss view. So just drag it. So this is the input file I just created and submitted for the optimization. Okay, so then we will see that optimized configuration. Okay, so this is that optimized configuration of the donor acceptor dye. Okay, so I will show you the input file for optimization. Just I will open with notepad++. So actually I mentioned the name dye 1, so I used this the memory 20 GB I mentioned, and ProShare also 40. If you are using the desktop computer, just you can change into the 6MW. Okay, here you can mention 2. Okay, that's enough. So here I am using B3LYP functional for optimization. So this is the optimization frequency keyword. Okay, then you have to give name, then you have to one space, then you have to give the charges of the total charges of the system and the spin multiplicity. These are the Cartesian coordinate of that molecule. Okay, so these are the atom present in the system. So after that you have to put 0, then you have to give your basis set. I have given the 631 G star basis set. Okay, then you have to give 4 star, that means end of the base set and end of the input file. Okay, then you can submit this file to your desktop or server supercomputer. You will get your corresponding output file. Okay, so that's all. So this is the output file. So this is the optimized geometry. Just you can save this geometry for your absorption energy calculations. Okay, that's all. So then we have to do our UV visible TDDFT calculations. Okay, so this is the input file for UV visible calculation. I will show you this one. Okay, first like your optimization file, same only, just you have to give some different keywords. That's all. The first one is chk equal to dye 1. Just I given the absorption calculation, just I will given that ABS. So here memory also I given 20 GB, here 40 and ProShare. So already I told you, if you are using desktop you can give 6 million words, here 2. Okay, that's all. So this is the theory I used for that TDDFT calculation. So if you want to use different kind of theory, you can also mention. Okay, yeah, I earlier shown that slide as that they use a different kind of functionals. You can use that one also to check your vibrational UV visible absorption spectra. Okay, then you have to see this is the UV visible spectra keywords. Okay, you have to mention TD equal to singlet comma n state 30. So you can also give 60 also. I think 30 is enough. Okay, if this is more than enough, you can use enough. So why you are giving your singlet? because we are doing the absorption energy calculation only. That means we have to give the singlet. If you are using emission spectra, you have to give triplet here. Okay, that is different kind of keyword we have to give. I already made one video for fluorescence and also emission calculation. If you want to know, you can watch that video also, you will understand easily. Okay, then you have to give pop equal to full. So this is why we are giving. So if you give this one, you can use one software is there, Gaussian. So we can visualize our UV visible spectra using that software. That's why I mentioned this keyword. This is very important. Then this is the solvent medium. Okay, so if you don't want to use solvent medium, just you can remove this one. Just you can use gas phase UV visible spectra. So I want to improve the solvent correction, so that's why I use the solvation model here. Okay, so solvation model, you have to put SERF equal to PCM comma read and solvent equal to ethanol. So if you want to use any other solvent like water means you can type water. If you want to acetonitrile means you type acetonitrile, the text. Okay, so that will automatically take that Gaussian calculation, will do the solvation under the solvent. Okay, that's all. This is the important UV visible calculation. So then you have to give space, then you have to type your name of the system, then you have to give your total charges of the system 0, then multiplicity 1. Okay, this is the optimized Cartesian coordinate. Okay, so you have to use for your UV visible calculation. So this is the what are the atom present in the molecule, then you have to put 0. Then you have to give your basis set 631 G star. So if you want to use higher basis set, you can also use it. This is no problem. So finally you have to give 4 star and you have to give enter, then only the calculation will go, otherwise you will get some error. So that's why I always give some spaces after finishing the input file. Okay, so that's all. You can submit this calculation to your desktop or Windows server, so you will get your UV visible TDDFT calculation output file. Okay, so this is over. So now we will see our output file. Okay, so first we can see with Gauss view. So this is the calculation I completed. This is absorption calculation. Just I will drag into here. It will open. So this is the molecule. So now we will see the result. Okay, so what you have to do, just go to result. You can see different kind of things here. You can see UV-VIS. Okay, just click it, you will get your UV visible spectra. So I think this is look like somewhat not good things, so we can make it nicely with one more software is there. I will tell you how to do with that one. Okay, here we can find what are the strong oscillator strength peaks. Okay, so you can see here, so this one the strong peak, so this is the second one, this is the third one. Okay, these 3 peaks are strong absorption peak with high oscillator strength. Okay, so in the UV calculation we need to take the high oscillator strength only for calculation for publication, because we do not consider the lowest oscillator strength. That is not useful. We always should consider the highest oscillator strength peaks. Okay, that's all. So now we will see the result, TDDFT results. Okay, so just to open with the notepad ++, you will see like that. So if you go down, you can find that normal termination of Gaussian calculation. Okay, so this is the one we have to check always. So if you getting any error means the calculation may not completed, just you have to do redo. Okay, so now we will see our TDDFT results. Yeah, so you have to come here. Okay, excitation energies and oscillator strength section. This is the UV visible results. Okay, so here you can see 3 state with high oscillator strength. This is the excited state 1, this accelerated 2 and this accelerated state 3. These are the 3 one. I already showed that image now, you can see. So 1 2 3, this 3 only, this 1 2 3. Okay, so we are going to only use these 3 peaks for our TDDFT calculations. Okay, so here you are only show the numbers. So 117 means you may not know HOMO or HOMO -1 -2. This also LUMO. This is LUMO +1 or +2 +3. You don't know, so you need to know this first. Okay, for that what you have to do, just to open that optimized file. Optimized means that UV visible result. Just already open that one. So this is the log file of that UV visible calculation. So here you have to go to tools, click MO. Okay, if you click MO means you will get that corresponding MO arrangements. Okay, here you can find your numbers. Okay, here you can see 117 118. So here 117 118. So 117 means HOMO orbital. Okay, 118 means LUMO orbital. Okay, this is the HOMO, this is the LUMO. Okay, this is the HOMO to LUMO transition. Okay, so first one. Likewise you have to see second one also. This is the excited state 2. Okay, here you can see 116 118. So 116 is here. Okay, so this is the 116. This 116 means HOMO -1. Okay, this is HOMO means this HOMO -1 -2 -3 -4. Okay, likewise this is the LUMO means this LUMO +1 +2 +3 +4 +5, like that it will go. Okay, so here excited state 2. Okay, here 116 means HOMO. Okay, HOMO -1. Okay, this HOMO -1 to LUMO. Okay, this is HOMO -1 to LUMO. So this is 117. Okay, this is HOMO to LUMO +1 119. So 119. Okay, likewise you have to check your orbitals. You need to match with this one. Okay, likewise you have to do. So I already matched like this. I have made one document for you. Just I will show you. So this is the one, that document. So here the important things is you have to take this energy. Okay, this is the very important, and also this is the another energy important. This is the nanometer. Okay, this is also very important. This is the oscillator strength. Okay, so I already made the table. Here you can see here. So first one is the system, the state. Okay, this is the state S0 to S1, like that. Okay, so HOMO, S0 means HOMO, this is the LUMO. Okay, S1 means like that. Okay, so here assignment I mentioned HOMO to LUMO. Okay, likewise. And then here you can see coefficient. Okay, this is the coefficient value. So in this coefficient value always people will give the in percentage. Okay, so for that I have calculated the percentage. Here you can see, just you can take this number and square it, and you can also after the squared value you have to multiply with 2, then that value you multiply with 100, you will get the corresponding percentage of that contribution. Okay, HOMO to LUMO contribution. Likewise you can also do S0 to S2 and S0 to S3 also. Okay, all transition you can calculate and you can put your value. Okay, here the energy you can see, this is the energy 2.04. you have to give this energy. So wavelength, corresponding wavelength, this is the oscillator strength 1.0860 I mentioned. Likewise you have to check the second one. So second one, the 2.97 something, you have to give this one. Then wavelength also you have to give here, and also oscillator strength. Likewise you have to check that higher maximum oscillator strength. Okay, you can make the table like this. Okay, so lower oscillator strength, no need to consider that one. Okay, this is the important things. So you can also do like this. This is very easy and also simple. Okay, so that's all. So now I will show you how to get your UV visible spectra figure. This is very necessary for publications. Okay, so for that what we have to do, just we will close these things, no need. So this is our optimized UV visible spectra output file. So for that we need to open our Gaussian software. So I will tell you one important things. So this is the Gaussian website. So if you want to know more about the Gaussian, just you can read that things. So if you want to do trial version, you can also get a trial version, you can try it yourself. Okay, so we can do a lot of things with this Gaussian software. Okay, so you can try it. So we already open, so we have to upload our output file. Okay, just you can drag into this page, so we will get our absorption spectra. Okay, so you can see this is our absorption spectra. So how looks very nicely compared to the Gauss view. Okay, so this is the things. So we want to change this the energy unit, just you can change into nanometer. Okay, so wavelength nanometer. So then you can also set ranges. Okay, set ranges. Here you can see here maximum energy 900 is there. So we can make into 800 from here we can make 200. Okay, so okay, so we will get good configuration. Then if you want, you can edit, you can right click in the spectra and you can edit page. You can see here. So if you don't want that lines, just you can remove, it will don't show. So and also if you want to reverse that this x-axis, just you can go to energy axis, you can uncheck this one, it will reverse. Okay, this is our spectra. So already shown, this one is the highest oscillator strength, this second one, this third one. Okay, like that we can get. So if you want to save this figure, you can also save. Okay, so for that you have to go to export image, go to plot, export image. So it will save as a BMP image. Okay, so just we will save it first. Okay, just we can save it, so we can leave. No, later we can see that one. So here I am going to tell you one more important things. So if you want to see your orbital, you can also see here. So just you can click this plus zoom and you can click again and again, it will create a zoom. So if you want to, you can also adjust here. So again you can click zoom, it will show. Okay, so okay, this is enough. So I think this is the HOMO, this is the LUMO. Okay, so this is the first transition. So here is highlighted here. Now you can see 606,491. The oscillator strength is 1.8. This is the first one. This HOMO to LUMO. Okay, so this is HOMO to LUMO transition showing here. So if you click second one, so you can see here, this is the corresponding transition one, this is the one. So this is the second one. Okay, so likewise if you want to click third one, you will see different kind of transition. Okay, like that you will get from that. So one more things I want to tell you, important things. So if you want to get your NTO orbitals, that means natural transition orbitals, so you can also get it. So we can see only the first one. So if you click first one, so here if you click first one, then you can go here NTO view. Okay, just click NTO view, just you can click calculate 3D surface. Okay, so it will create your image. Yeah, this is the hole, this is the particle. Okay, this is the transitions in orbitals. Okay, So you can also save this image of you can use for your publication. So just you can zoom it like that, zoom out, you can save this also. Okay, I think here also you can see ISO value, you can adjust it if you want. Okay, otherwise no problem, just you can export image. Okay, we have created. So this is the things. So I will share this input output file to you. You can also see and analyze and do your UV visible TDDFT spectroscopy. Okay, so that's all. Thank you for watching my video. If you like my content, please like, subscribe, comment and share, and also please click the bell icon for future video update. Thank you for watching. Thank you so much for your